Hi, I am Deepak Dey. I am a distinguished professor in the Department of Statistics at the University of Connecticut in Stores, Connecticut, USA. Today I will talk about Bayesian estimation for the normal problem. That means when we have a random variable which has a normal distribution with mean mu and variance sigma square. On top of that, we assume here that sigma square is known. And we already described this problem, and goal is to find the posterior distribution of mu given the data under the assumption of sigma square known, and we'll step by step develop how this can be achieved. And we'll show that the posterior mean will be a convex combination of the prior mean and also the data mean. In today's lecture, we'll talk about Bayesian analysis of the normal distribution. In particular, we'll talk about Bayesian estimation of the mean of a normally distributed random variable with known variance. The benchmark is the maximum likelihood estimate for the normal distribution for known variance. That because you are very familiar with the maximum likelihood method of estimation, which is the classical method. So suppose yi are independent random variable, all are normally distributed with mean mu and variance 1, for I is from 1 to n, where n is typically the sample size. The likelihood function for mu will be L mu given that y is equal to product of the normal densities, which is 2 pi to the power minus 1/2 exponential minus 1/2 yi minus mu square. Now if you take the logarithm, so it's a log of L mu y, will have the expression as shown as sum of 2 pi to the power minus 1 minus half yi minus mu square. To find the MLE, we take the derivative of minus log L, log minus L, and we set the result equal to 0 and solve for mu. And when we solve, we get the solution mu equal to sum of yi over n, which is the sample variance. Now, the normal model with known variance problem, we can consider the following. Suppose y is normal mu with variance sigma 0 square, where sigma 0 square is a known constant and mu is unknown, because we assume variance is known. What would be a good prior to choose for mu? Because we are in a Bayesian framework, we have to choose the prior for mu. What properties should that prior will have? A reasonable choice for the prior distribution of mu will be again a normal. Why? Because the normal distribution is a good choice. Why? Because the normal distribution is quite flexible. The prior mean can take any value along the real line. The prior variance can be chosen so that our prior beliefs are or are not influential determinants of the posterior mean and variance, because it may be a close representation of our prior beliefs. If our prior beliefs are symmetric and unimodal about some point along the real line, because it is conjugate prior, so the posterior will be again a normal. And the detailed calculations are given in the slide. Just to start with that, let y be normal with mean mu sigma 0 square, and the prior we choose mu to be normal with mean m and variance s square. So in that case, one can show that the posterior distribution of mu given y is proportional to the prior of mu times the likelihood of y given mu. And after simplification, you can write down, there are some detailed calculations given in the slide. So one case is the drop multiplicative constants. then expand the squares and combine the two expressions. We collect terms and use the basic properties of exponent and then get the last expression. And then after simplification we can get the posterior distribution will be mu given y is proportional to the exponential of that term, and you get in the slide the final expression. To achieve that, we multiply throughout by sigma 0 square s square, then multiply and divide by s to the power minus 2 plus sigma 0 to the power minus 2, and inverse of the whole thing. And then we do some cancellation of terms, and then finally we simplify to get that expression. Okay, now in this slide you see that after all the simplification, the posterior distribution of mu given y will be simply normal with mean mu hat and variance sigma hat square sub mu. And this is the final answer for the posterior distribution of mu. Okay, so now here is a quick discussion of the normal model with variance known and a normal prior. The posterior mean, which is the mu hat, has the expression that given here in the slide, which is m divided by s square plus y divided by sigma 0 square, whole thing divided by 1 over s square plus 1 over sigma 0 square. And that's clearly, we can see that it's a weighted average of the prior mean and the data. So it's very important for you to remember the posterior mean of mu, which is mu hat, is nothing but the weighted average of the prior mean and the data. The weights for these two component y's respectively, the prior precision, which is 1 over s square. As you know, s square is the variance, so 1 over s square will be the precision. And the data precision is 1 over sigma 0 square. We have already observed this sort of weighting between the precision and the prior and the precision of the data before we studied some other distribution. The pattern occurs over and over again in a Bayesian framework. If we have more than one observation of the random variable y from the normal distribution with unknown mean and known variance, it is a trivial matter to extend this result to show that the posterior distribution of y given the samples y1, y2, yn will be again a normal with mu hat as the mean and sigma hat square sub mu as the variance of the posterior. So mu hat is again is m over s square plus n y over sigma 0 square divided by 1 over s square plus n over sigma 0 square. And sigma mu hat square again has the similar expression, and now only instead of 1 over sigma 0 square, it's n over sigma 0 square. Again, notice the weighting of the prior mean and the mean of the data. It's also notable that the fact that as n grows, the mean of the data swamps the prior mean mu. Therefore, for large n, the Bayesian posterior mean will be approximately equal to the MLE estimates. So this is a very important fact that as n becomes large and large, that is n goes to infinity, then the posterior mean will converge to the maximum likelihood estimate. So here we have a quick example. Question: what is the average blood pressure reading of a subpopulation of 20 adult men? Suppose yi denote the blood pressure of individual I, and assume that yi is normally distributed. Based on the national studies, we assume that we know that the standard deviation of y is 13. And that's kind of information based on the current data or past data on the national study. We relax this assumption in a bit. Let mu denote the average blood pressure of the group, that is the true blood pressure. So clearly the data is now yi, and for each patient, say I from 1 to n, yi is normal with mean mu and variance 13. Sorry, standard deviation is 13. We need a prior distribution to summarize our initial uncertainty about the value of mu. If we continue that example, we again have yi, I from 1 to n, mu with normal with mean mu and standard deviation 13. Now, why might it be possible to choose a normal prior for mu? Why might it be useful? What are the problems with using a normal random variable to describe the blood pressure data? What values should we choose from m and s square? What is the posterior distribution of mu? So we'll answer some of the question next. So suppose we have yi normal mu 3 and we choose the prior mean of mu as 0 and s square 10,000. S square is the population sample variance. What is the posterior distribution of mu? The posterior distribution of mu, again we know, is normal with mu hat as the mean and sigma mu hat square as the variance, where the expressions for mu hat and sigma hat square are given below, which follows from the previous slide. And after simplification or plugging the value, we can check that mu hat will be 128 and sigma mu hat square will be approximately 8.32. So that is the example. Now we'll move to the unknown mean and variance. Let's extend the model, normal model, to the case where the variance parameter is assumed to be unknown. So in the last discussion, we assumed from the beginning that the variance is known, but now we'll deviate from that assumption by making unknown variance scenario. So yi is now normal with mean mu and variance sigma square. So here note that both mu and sigma square are unknown. This is our first example of a multi-parameter problem. Like earlier we had only one parameter, even if there are two parameters present, but one was known. Now both are unknown and therefore it's a bivariate, or in particular it's a multivariate parameter model. The Bayesian setup should still look familiar. We can now write down the joint posterior distribution of mu sigma square given the data is proportional to the prior of mu and sigma square joint prior times the likelihood function y given mu sigma square. Note that we would like to make inferences about the marginal distributions, which is p of mu given y and p of sigma square given y, rather than the conditional distribution of mu sigma square given y. Ultimately, we would like to find a posterior distribution of mu given y, which is the integral of the mu of the distribution of mu given sigma square y times distribution of the sigma square given y d sigma square. So we have to integrate that expression with respect to sigma square. What should we choose for the prior distribution, joint prior mu and sigma square? We'll talk about different types of Bayesians choose different priors. For classical Bayesians, the prior is necessary. Choose priors that interject the least information possible. Modern parametric Bayesians choose the prior in a useful convenience. They choose prior distribution with desirable properties, for example, conjugacy. Given a distributional choice, prior parameters are chosen to interject the least information possible. And then the third approach is the subjective Bayesians. The prior is a summary of old beliefs. Choose prior distribution based on previous knowledge, either the results of earlier studies or non-scientific opinion. Now we'll talk about the classical Bayesians and the normal model with unknown mean and variance. So suppose y is normally distributed with mean mu and variance sigma square, where both mean mu and sigma square are unknown parameters, which we assume they are random variable from a Bayesian perspective. What prior distribution would we choose to represent the absence of any knowledge in this instance? What if we assume that the two parameters were independent? So the joint distribution of mu and sigma square is the product of the individual distribution of mu and that of sigma square. The classical Bayesian method tells you, again, we assume normal y is normally distributed with mean mu sigma square, and joint prior of mu and sigma square is product of that. That means they are independent. Now we assume that the probability of mu is flat, that means just proportional to a constant c for the whole range of support of mu from the real line. And p of sigma square, prior for sigma square, is 1 over sigma square, where sigma square is between 0 and infinity. Then the joint density of p mu sigma square will be proportional to constant times 1 over sigma square, which is simply 1 over sigma square. Are these distributions produce proper posterior? That's a very natural question, and we'll see how it does. So to do that calculation, we assume yi given mu sigma square is normal with mean mu and sigma square, I from 1 to n, and then the joint distribution of the posterior will be just 1 over sigma square times the normalizing constant times exponential of the things which are given in the slide. And it can be shown easily that the conditional posterior distribution of mu given sigma square and y is simply normal with mean y bar and variance sigma square over n. However, it still involves sigma square. So to compute the marginal distribution, we need to calculate the conditional distribution of mu given y, which will be the integral from 0 to infinity, the distribution of mu given sigma square and y, and integrate with respect to sigma square. It can be shown that after some algebraic simplification and identifying the probability distribution, it can be shown that probability of mu given y, that is the posterior distribution of mu given the data, has a student t distribution with n-1 degrees of freedom. Notice the parallel between these results and what we would find it in classical theory. Or more conventionally, we see the joint probability distribution of the standardized variable mu minus y bar over s over square root of n given the data has a student t distribution with n-1 degrees of freedom. From previous slide, we observe that the joint distribution can be written as mentioned in the slide, where s square is the sample standard deviation. Now a natural question will be, what is the marginal distribution of sigma square? The marginal distribution of sigma square, which we mean is the posterior distribution of sigma square given y. In that case, we have to eliminate mu. So we integrate, to get the expression, we integrate the above expression with respect to mu. And if you do that, then the posterior distribution will be inverted chi square with degrees of freedom n-1, which is an inverse gamma distribution with two parameters, n minus 1 over 2 and n minus 1 s square over 2. Now there are two different methods to sample from the posterior in this case. Method 1 is the sample directly from each of the two marginal distributions, and method 2, which suggests that sample a value from distribution of sigma square y given y, that's the first stage, and the second stage we sample a value from the distribution of mu given sigma square and y. Repeat these stages lots of times. So the key point here in method 2, which is very important because this will lead to MCMC approach. So first stage we sample a value from the distribution sigma square given y, and then we sample a value from the distribution of mu given sigma square y. So throughout following my lecture, you have understood that I have defined how to calculate and derived the posterior mean using the Bayes formula. First obtain the posterior distribution and the mean of the posterior to show it is a convex combination of the prior mean and the data mean on the assumption that sigma square is known. In the next lecture, we'll consider the case when sigma square is unknown, and then we'll do actually how to develop the prior for mu and sigma square, and then develop the new methodology for estimation of mean problem. Thank you.